This video is going to cover operations with complex numbers. And complex numbers, it's covered up here. We've kind of worked our way around it, so it's kind of hard to see. But the definition of complex numbers is up here. Complex numbers are basically when we have real numbers together with imaginary numbers. And when we do that, we have real numbers with imaginary numbers. They go in the form a plus bi. And that's what I wrote over here in the margin, that we have a plus bi, and the real number comes first when we write that number. So as we talk about operations with complex numbers, the first thing we would probably talk about would be addition. And so how can we add these two numbers together? Well, first of all, that square root of -9 needs to be simplified. And we've talked about how negative numbers, if it's a perfect square, because 9's a perfect square, if it's a perfect square, you just basically, when you take the square root of it, you just have an I with it. And so as we do this first one, we are just going to simplify that -9 down to 3i, and then we have a plus 6. And so we are almost done, but the problem is that we need to have it in the correct form, kind of like standard form here. So we need to have our real number first, and then the imaginary number after that. Okay, let's take a look at the second example. Same basic thing. So -18 is like -1 times 9 times 2. And so since 9 is a perfect square, we can factor that out. So this is going to be 3i radical 2. And then the 7, nothing we can do with that. Now the only thing is we want to have our answer in kind of the standard form here with our real number first and our imaginary number after that. And so our final answer here would be 7 plus 3i radical 2. So that covers addition. Let's turn the page. Adding and subtracting. What if we have more than just those two things in there? We've got some other things going on. So this is a lot like adding like terms. So on the margin I wrote down like terms because this is really similar to adding like terms. If we look at these, we have a 5 and a -2. 5 plus -2 is 3. We have a 7i and a 6i. Those are kind of like our like terms, so we add those together to be 13i. And again, we make sure that our real number is first and our imaginary number is second. Example B is a lot like that. It's just we are subtracting instead of adding. And so here we have an 8 minus 2, and we have a -3i minus 4i. And so as we simplify that, 8 minus 2 is 6, -3i minus 4i is a -7i. Okay, with multiplying. We do multiplying the same way, but it's just going to have another additional step of simplifying with it. Because I think we can see that when we multiply this, we are going to get a -20i squared. Now the thing is, if you look out in the margin, I squared is -1. And so if we're going to simplify this, this would really be the same thing as a -20 times a -1. And a -20 times a -1 is a +20. So the answer on that one comes out to be a +20. And so this is going to be kind of helpful that we start to lose some of the i's. If we multiply two i's together, we lose the imaginaries and they become reals. Number 2, we are going to double distribute this, FOIL this. So as we do that, what we're going to get is 2 times -3 is -6. 2 times 5i is 10i. 3 times -3, 3i times -3 is a -9i. And then 3i times 5i is a 15i squared. Well, we just talked about how I squared is -1. So 15i squared is actually equivalent to a -15. So now I'm going to add my like terms again. That is, I have a -6 and a -15, which combine to be a -21. And I have a 10i minus a 9i, and that adds up to be a +i. These next two examples are going to be similar. So why don't you take a minute right now to multiply out number 3 and see what you get when you multiply that out. Okay, on number 3, when we multiply this out, we get a 24 minus 18i minus 20i plus 15i squared. Well, plus 15i squared is actually minus 15. And so if we add our like terms, we have a 24 minus 15, and 24 minus 15 is 9. We have our two like terms in here, a negative 18i and a negative 20i, and those can combine to be a negative 38i. Number 4 works out similarly. We have a 15 minus 6i plus 35i, and minus 6i plus 35i combines to be a 29i. And then on the end, we have a minus 14i squared. Well, that's like plus 14. So we really have 15 plus 14, and that's 29. These next two examples are going to be a little bit different. They're a little bit, if you look at them, they should look a lot like what we've been doing with perfect squares. And it's going to work a similar way, because when we multiply these, those middle two terms are going to drop off. And so when we multiply, we get 16 minus 20i plus 20i. Well, the minus 20i and the plus 20i are going to drop off. And then we have minus 25i squared. So what we really have, these two middle terms drop off, we really have 16 plus 25. And 16 plus 25 is 41. Similar thing over here with number 6. We're going to do it the same exact way. 64 plus 16i minus 16i, they drop off. And then we have a minus 4i squared. So what we really have, those drop off. We have a 64 plus 4, and that is 68. So that becomes quite helpful for us, because what happened, we had an imaginary, we had complex numbers to start with, but our answer was a real number. Didn't have imaginaries anywhere. That's actually very, very helpful. And so we call those complex conjugates. Complex conjugates are when you have these sets of the same exact numbers, but one of them's plus, one of them's minus. And that's what we had on number 5. 4 and 5, one of them plus, one of them minus. Number 6 was an 8 and a 2, one of them minus, one of them plus. Doesn't really matter which the one comes first as far as the plus and minus goes. So the conjugate here, 3 plus 4i, its conjugate is 3 minus 4i. Take a second. Do you know what this one is going to be on letter B? 8 minus 5i, what's the complex conjugate? Hopefully you said it was 8 plus 5i. Okay, I'm going to skip down a little bit. So this complex conjugate concept right here, let's skip down to example D, or part D, where it says rationalizing the denominator, because these two concepts really are going to work together. So I mentioned a minute ago that the advantage to the complex conjugates is that you started with a complex number and you ended with only a real number. That's helpful because we have this thing called rationalizing the denominator. And you remember that phrase from when we had radicals in the denominator. You're not supposed to have a radical in the denominator because a radical is not a rational number. And we also don't want imaginaries in the denominator because they are not rational either. So we only want rational numbers in the denominator. So the way to get rid of the imaginary is to use these complex conjugates. So we're going to come down here, we're going to use complex conjugates. I'm actually going to do number 2 first because it looks a little bit more like the ones we were just talking about. So I look at this denominator, I see 2 minus 4i, and I know I need to multiply by the complex conjugate. Well, what's the complex conjugate there? Okay, hopefully you realize the complex conjugate is 2 plus 4i. And if we multiply that in the denominator, we also have to multiply it in the numerator. So we need to take a minute to multiply out our numerator entirely, as well as multiply out our denominator. And so take a minute to do that. Just multiply that out and see what you get in your numerator and your denominator. And then go ahead after that and simplify those and see how far you can simplify this. Okay, when you multiplied it out, you should have simplified it down to 10 plus 22i minus 4 over 4 plus 16, because 4i squared is negative 4 and negative 16i squared is positive 16. Okay, we then need to combine our like terms, and we get down to 6 plus 22i all over 20. And then finally, we need to reduce our fractions. And we talked about this in most of the hours, and we'll continue to talk about it. But you can distribute and factor out whatever is the greatest common factor. So I see that 2 can go into all of those numbers. So I'm going to divide everything by 2. And so my final answer is down here, 3 plus 11i over 10, because now it has been reduced as far as it can go. And remember that our real number comes first, our 3 comes first because it's real, and the 11i goes on the end. Now let's backtrack and look at number 1. And the reason I wanted to do number 2 first is because that denominator looks a lot more like what we're used to. Number 1 is actually a little bit shorter, but it looks different. So you just aren't quite as ready for it maybe. But I think we can do it. So we have a negative I. The complex conjugate for a negative I is a positive I. Now remember, we're multiplying here. So we're going to multiply the numerator and the denominator by a positive I. And so in the numerator, I just get 3i, and then I distribute my I times 8i, and I get 8i squared. In my denominator, I have a negative I squared. I'm going to come over here to the margin because I'm kind of running out of space here. So I'm going to come over here. I'm just going to simplify a little bit as I go. So I have a 3i, and then this is minus 8. And in my denominator, I have a negative I squared. Well, what is negative I squared? Well, I need my negative to stay there for just a second. I squared is negative 1. So what I really have is a positive 1 in the denominator. And so the only last thing is to make sure my real part goes first, my imaginary part comes second. So this simplifies down to a negative 8 plus 3i. And so again, the goal was to get that imaginary number out of the denominator. So now we have an answer that does not have an imaginary in the denominator. And once again, I'm showing all of my steps, but I think by now some of you are probably catching on that that's supposed to just be the negative of whatever number it is, and you don't have to show that step if you don't need to, that's fine. Okay, now that we've talked about rationalizing denominator, now we're ready to take a look at some of these problems. And these are solving some equations. Well, as we look at these two, you should notice that the discriminant would be negative. So a couple things. First of all, I would think, okay, can I factor this? I'm looking at this, and I'm looking at my 5 and my 2. There's no way. I cannot factor that. A 5 and a negative 2, that's just not going to work. And if I can't factor it, my only other option is to do the quadratic formula. Before we even do that, though, realize that because the discriminant is going to be a negative number, if we put these in our calculator, we would get something that tells us it's no real solution. And your calculators each say it differently somehow. Invalid domain, domain error, things like that, that tell you what that means is no real solution. That means there's no real solution, but there are imaginary solutions. And if you look over in the margin, I drew a little graph just as a sample. I haven't graphed either of these, but I know what they would basically look like is it would basically be a parabola, and I call these floaters. It's like floating up there. It does not have x-intercepts. It will still have a y-intercept at 5. So that y-intercept right there is going to be right about 5, but it does not have any x-intercepts. So we're going to go ahead and do the quadratic formula, but our quadratic formula answers are going to be complex solutions, that is, they have imaginaries in them. So go ahead and set this one up, example A, with the quadratic formula, and let's kind of work through here and see what we get. So you start plugging in, and then we want to go ahead and simplify this because, again, our calculator isn't going to simplify it because it's going to tell us it's no real solutions. So I'm going to kind of go step by step and see what we get step by step. In the discriminant, I have 4 minus 20, that's a negative 16. Well, 16 is a perfect square, so that's going to come out pretty easily. So I have 2 plus and minus 4i all over 2. And once again, that's supposed to be a 2. Those, all three are divisible by 2, so I can divide that 2 into each of those. And so I simplify that down, and I get 1 plus and minus 2i. Same thing on example B. We need to set this up as a quadratic formula problem. Our calculator won't do it because we end up getting a negative discriminant. And so we have to go ahead and work it out kind of step by step and come up with our solution. Okay, so mine's probably a little bit hard to read here, but when you plug it in, you end up in the discriminant, you get 100 minus 140. Well, that's a negative 40. And negative 40 goes down, negative 1 times 4 times 10. So that is a negative 10 in front, and then plus and minus. Negative 40 breaks down to a 2i radical 10. And again, it's all over 2. So the last thing, once again, is to divide both of these. Divide by 2, so we get a negative 5 plus and minus I square root 10 as our final solution. Okay, we worked through a lot of different types of problems today. Just to review some of the things we did, we talked about adding and subtracting, that you're basically adding like terms. We talked about multiplying, and make sure you realize when you multiply that I squared is equal to negative 1, and so that's something that we have to pay attention to. That, which actually turns out to be pretty helpful, because when we get to complex conjugates, we started with complex numbers, we ended with real numbers. So that's really helpful that I squared is negative 1, because we use that when we simplify radicals, which is down here in part D. And then finally, we did a couple of examples where we were using the quadratic formula, but the quadratic formula came out with an imaginary solution. We actually saw that a little bit the other day on our Big Ideas Math homework, and some of those answers in the back were printed as an imaginary solution, where we were just saying at that point, no real solutions. So that is everything that we're going to cover on imaginary and complex operations. We've covered all the operations there are. This I cycle is blank right now, but we cover that in class, so you should already have that filled out from class. We will continue to work in class on some of these operations, and you'll have opportunity to ask questions about any ones that you need to ask questions about.